that they have been using are causal models. That is, that they only predict the next token from the last tokens, rather than saying marking a token out and being able to predict from both sides. Because they're considered sort of one direction only causal models, you can always have time increasing. X is in control system theory is the state space. So it is all that is known about the environment. So in our case, this is the initial prompt in the LLM. The LLM waits, and essentially what is being calculated out to the point that we want to produce the next token. So all of that is essentially considered the state space, the model, the initial prompt, and the first one through forward. U is the input space. So this is what we can do to control the aircraft, or in this case, the large language model that we want to control. And what they do is they use the U, or the control space, as being a prompt that you place in front of the prompt that you've already got. So now what we're doing is we're prepending something through our initial prompt to try and make the model do what we want. And then there are some control system, some control systems also have an output space, so you can measure what they output. So Kalman filter or something like this is in this case. And sometimes they have an output map, so you can read out, what the state of the system is and what you're doing. So we're in that state. We have an output space and an output map, and a lot of the examples we can think of will have that as well. So if you can jump back to to the top of the paper, page 1. So looking at large language models under this lens, they have x0 in the abstract here, and sometimes in some of the graphs they refer to it as x_0. This is so I'm going to say this is the prompt that is, not the prefix, is the prompt that is being presented to the system. And essentially what they're saying is they're trying to estimate and get an idea of how much can we control the next token after this prompt, given a particular large language model, given this prompt, if all we can do is inject earlier tokens in front of it. And then they also start looking at how many tokens that they need to insert before it. So this is the K value here, is how many tokens before it they insert. Great. Okay, and now, and also if anyone has any questions, please jump in. So now what I was going to do was to say what I was going to say. So the initial state sequence, x0, yes, we've done that. They prove an upper bound on what you can get to. And they demonstrate a lower bound. The code is available at the bottom of page 1. The code is available in GitHub. I have a chunk of it running and working, but not all of it yet. And I think it has something to do with the fact I'm trying to run it on a Mac rather than NVIDIA. What are we doing? So the contribution that they say, this is on page 2. They're trying to look at the line 4. They're trying to look at line 3. Sorry, they're trying to look at control theory and controllability, stability, and observability. And they've mentioned these in the appendix, which we just took a quick look at. Okay, and then they now go in the paragraph starting our empirical results. They draw some findings that they've got, and they do 3 major experiments. And what they're generally doing is they're sampling from wiki text, which is a body of text from essentially from Wikipedia, think of it. And then sometimes there are questions after this saying, you know, a block of text and a question. All they're doing is they're just sampling from the text. And so they're using this as the prompt, just a set of tokens that we should get, and that it would be reasonable to expect that they're in the training data set. And they're saying now, what kind of prefixes can we put in front of this to get what token afterwards? At first of all, they say, can we get the ground truth token? So the token that should be there, and they find that they can get there quite efficiently. I think it's 97% of the time. Then they start flipping the problem on its head a little bit, startly taking the next. So if I took the initial prompt, ran it through the large language model, and took the outputs and the logits of those outputs, I can select the top 75 next tokens, and then I can see how often I can get one of those tokens. So that's another experiment they do. They, you know, can we get the correct answer? Can we get the top 75% answer? We would expect if large language models are sensible that you would want both of these things. The third experiment that they do is they then flip this on its head, and they start seeing what, if we pick a random token, can we produce a random token next? And so again, what they're doing is they're taking a set of an initial prompt, they're prepending things to that prompt, and they're saying a random word from the vocabulary, which might be a Japanese symbol or a, you know, or any symbol from the vocabulary. Can we get that? And with how long a prompt do we need to get that? So yeah, actually describes this. It describes that there in post-state LLM. So the definition on page 4, halfway down page 4, essentially just repeats what I said before about the control space, the control system and the state space. And then they produce some mathematical proofs on page 6. And so essentially in the mathematical proofs, I think the proof is actually in the appendix. But what they're doing is they're taking the attention mechanism in the large language models. And you've got the WQ, K, and WV in the top of the screen, definition 6. And essentially by breaking the system down into the prompt and the prefix, and then following this through the maths, you start finding out that you can break each one of these matrices down into 4 matrices. And then they essentially follow that through and start showing what the length of the maximum length must be. I think that's the way it worked, to show an upper bound on the bound as to what the prefix must be in order to produce a particular token, or the reachable set, essentially what they're saying. So can we say whether a token is reachable or not based on these? The reviews in open review said that this was like a good proof, but that it doesn't prove something that is surprising or that we can leverage very well. I think is my interpretation of the review's comments. So then they went on and started doing the empirical studies. So this starts showing what you can and can't get. So for each study they started doing it, they did it on 3 models. They did it on a 7 billion parameter falcon, a llama 7 billion parameter, and a Falcon 40 billion parameter model. These are all left to right models, all causal in that way. They started producing an algorithm here that's just on the screen here to show you how they actually start producing the prompts. In the first one, for k equals 1 to 3, what they do is this is one of their contributions. They simply just run the model forward for the full vocabulary. So I have my prompt for every token in the vocabulary. I just run the model forward for each token, so 50 to 50,000 times forward. Then I pick the best token for that location. Then I do again and again, and they said that this was better than the other methods that they had. They then revert back to, then they continue with a greedy coordinated gradient search. And so this is from another paper that you can go into, and this is included in their code. And what this does is it takes a batch of inputs, and again, it is trying to find tokens to prefix of a certain length. It takes a certain length of tokens. It takes a batch of inputs and answers. And I don't fully understand this yet, but it is what it is doing is it is driving this forward, looking at the outputs, the logits, and then trying to, I think it's picking the maximum of what is output, but it is using this as an input token and then swapping them randomly on the input. So that's a horrible definition of mullered explanation of this, because I haven't had the time to go into this properly yet.
So they use gradient information to choose the next token, or to choose the prompt?
They do, yes.
It's interesting.
I didn't see, it didn't really, it wasn't obvious to me what they were doing. I didn't correctly understand it. I was comparing this with the code, and I didn't yet go back to the original paper. The code that they say, there's comments in it suggesting that it's come from the original authors of this method. And the other interesting thing about this is, there are two other interesting things I found as well. One is that it doesn't seem to be, this algorithm is used for jailbreaks. It doesn't seem to be trying to produce anything afterwards. Like it doesn't have a, make it say unsafe words, or make it say, it doesn't have any kind of data in that way. It just has some text, and then it's trying to predict forward. It has the answers, so it has the prompt, it has what was ground truth answer, and from this it is working out what to build into the prefixes of a certain length, and it's randomly mutating tokens between these. Yes, Damon.
So is this, if I understand this correctly, it's like a way to evolve the system prompt to ascertain that the output that you want is going to be generated from the input that you provide?
That is my, I can't put my hand on my heart and say that's what's happening, but that's my hunch that that's exactly what's happening. So given prompt, ground truth prompt, ground truth answer, try and find the prefixes that make the ground truth answers more likely. And then
wow. So it sounds like a massive attack vector, or like a really good attack method, I guess. Yeah.
Yes, absolutely. And then, so then once you do that, you change the prompt, and then the model will do what you want rather than, I suspect, is what the conclusion of this is. It's rather clever in that it is bypassing, so much of the fine-tuning guardrails or efforts that are tried to put on around the LLMs at the moment. Yeah, so I did find this quite fascinating.
Yeah, I wonder if in the future, actually, the thing I was wondering when I was looking into this is, I wonder how sensical the prompts are that are generated. Maybe I know there are only 10 tokens, so say this works for like a large prompt that you're creating. Say you write one and then you want to edit it to optimize it like it. I wonder if it would make sense to you after the optimization, or if it would just look like gibberish, but it gives you the result you're looking for.
I can answer that, and it's often it looks like total gibberish. Like a kanji token, and then a weird math symbol, and then the word, greed, and then yeah.
That's interesting / crazy.
Absolutely. Damien.
I was curious, within the paper, did they mention anything about generalizability of this approach, in a sense that would a similar system prompt that has been evolved using this approach work for, let's say, a class of different inputs?
Yes, because they're doing it on a batch level. So they don't take one prompt and one output. They actually do it in a batch across multiple outputs. And then they've actually shown that this works across the 3 language models that they tried. And then they tried that on commercially available LLMs that you can't actually get access to. And yes, you could jailbreak them quite easily.
This is really crazy. Wow. Really cool.
Yeah. Yeah, it stabs at the heart of, yes, we'll be able to make LLMs safe, and yes, LLMs are reasoning engines, because I'm not of the opinion that they're reasoning engines.
I mean, what you just said is pretty definitive proof of that, unless they've learned to speak English in a manner that's like so intelligent and complicated that it's beyond our comprehension, which I just don't believe.
Yep. And then if we go down to page, are there more questions here or comments? Yeah.
Nothing for me.
Okay. If we scroll down to page 8, which is it's got some graphs on it. So I found this quite interesting. It took me a while to stare at this and understand or get an idea of what was going on. But in the graph of top left, you can see that they do go beyond. Okay, so the prompt length K is from 0 to 10. So this is the prefix that we're doing. And so I felt for clarity they should have mentioned something that they mentioned elsewhere, is place your prompt here. Roger Federer is the, okay, and we want to make that actually say something, a particular word that we pick, let's say greatest, or is 7, or that's the makeup of this. So the U here is, sorry, I'm going to jump around in terminology because I feel they do a little bit, but so in the key of the top left graph, the different colors, these are the state of the input, which is showing you what the as they're interrogating it, like, so they've used the algorithm that we were talking about before. So they're using the initial prompt, which would be Roger Federer is the, and the length of these is either 8, 10, 16, 22, or 32. If I understand the code correctly, what they're doing is they're doing this truly randomly. So they're picking this randomly throughout the text, the wiki text. And so that they're not stopping at a nice place or a bad place, or starting at a nice place or bad place. So these 45% of words in English are stop words. So there is a chance that the next token to be predicted is a stop word. And what they're trying to do here now is check what can we, with a prefix, can we produce the correct word? And they can quite easily, just with a prompt of 1, you can get, with a prompt of 1, you get 40% error. A prompt of length 2, a prefix prompt, you get, say 30% error, and it drops down quite noticeably. I did notice that the between 2 and 4 on the top left plot, the order of these lines is from is in the same order as the key, but just reversed, which to me made me wonder whether the as the length of the text increases, the error increases, which I found odd, if that makes sense. So the longer is the snippet that we're taking, slightly longer, we get slightly more error. I also noticed in the, so that was the plot of can we get the correct word. The next experiment they did was they they take one of these snippets, they push it through the large language model, they take the 75 most likely next tokens, and then they check how often can they get, is it on 25? So it's 25 samples they've done this for, and how often they can get all of the, I don't know this, whether they can get all of the tokens or any of the tokens in the top 75%. I'm not sure. Sorry, I didn't check that. And then the last one that they did was the bottom right plot is given that so they push things through the large language model. They look at the, so 0 here is the least likely token, and they say it both ways, so I'm not quite sure which one it is. 0 is the least likely next token. 70,000 is the most likely ranked token, could be the other way around. And then they started showing how, given the rank of the next token on the ground truth of our Roger Federer is and what was produced next, how likely are they to control this? And it shows that they came to the conclusion that it's quite uniform here. The probability of the next token didn't sort of sway, and that you can only produce more likely tokens or least likely tokens. Interestingly, in the appendix, Llama does show a little bit of a pattern, but broadly it is still quite linear. And what else? Okay, so the other thing that I marked up here, but you can't see it, is that, so kind of in summary, with the prompt length of k less than or equals to 10, the correct answer can be found 97% of the time. Sorry, the top 75, that's right, now I've got to remember this. The top 75 tokens in the top 75 can be found 85% of the time. And a random token from the entire vocabulary can be found 46% of the time. And it seems to say to me that so with this, we can start saying that as a prompt, 1 + 1 equals. Now they're kind of saying that 46% of the time across wiki text, I'm not sure maths would follow, but we can insert anything we want there. 1 + 1 = 3. And that's, or 46% of the time we can we can control it. Which really is far higher than I thought we would be able to get, because this is text that the language model has seen before, if that makes sense. So we can knock it off its learned hyperplane manifold. Yeah.
You bring up a good point, because when I was reading this, I was actually thinking, like, why do we care so much about this reachable set that we could achieve? Like, we could, because I think, what is it, like a controllable system is one where you can reach any state in the system from any other state, which is definitely not controllable because you can't remove tokens. But I mean, why do you care about? But I guess the point is, you actually want to have a limited reachable set for a specific input to make sure that, like, if there's like a region of that set that's unsafe or dishonest, that you can't reach it from there.
So if I can prove that the reachable set is reasonable or is not harmful, then all of a sudden our system is far more like safe or controllable, like in that way, right? So it's autopilot in an aircraft, even if it can't deal with, dropping 10,000 feet in a second. So not everything is reachable from everything else, but within the realms of normal physics, it can cope with that. So then we deem it safe. We're happy to fly it. It will maintain control. So in the same way, absolutely. So it's, for me,
In
this
terms
was,
of these, oh,
yeah.
sorry, go ahead. In terms of the experiments, one thing I didn't understand is, like, and this actually goes back to a question I had about reachability in general, because I was like, okay, if every single you put your prompt in, and then you want to figure out what's the probability of each next token. For any token where the probability is non-zero, it's reachable, right? I think that's the definition of reachable. So,
Yes.
then I was like, I kind of expected that for any token, I mean, for any prompt, you'd probably have like a non-zero probability for any token, but maybe that's not the case. It's just that I always thought like, okay, they're just super small, like floating point error small kind of values for most tokens. And then the thing I was wondering here is like, are they sampling, and do they view that as a valid way? Because if I wanted to figure out what was reachable, I would just look at those probabilities. I wouldn't sample.
I think the probabilities are non-zero. I think they are very small, and I think I think it's that problem that in the key part of the LLMs, I believe that they just go and they start sampling for the next token. They do have some kind of distribution, and they do sample from it. And I don't know if there's a cutoff here in different language models or in different implementations, but as you want to train the model, really you want that to be very wide open. So then as so they do say in the beginning of the paper that maybe cross entropy loss is not the one that we want to go for because it has these issues. I mean, I'm stretching a little bit of what they say there. But. Yeah, this is the part. Our results suggest that prior likelihood-based metrics such as cross-entropy loss cannot guarantee an exclusion from the reachable set, emphasizing the gap in our current understanding of LLM systems and control. Implications of our results and open questions in LLM control theory are further discussed in section 6. So this is quite a crux to that. This is quite a I didn't, I glossed over it when I first read it, and I started realizing that this is quite a key element in the paper.
Now that we've been discussing this, I think that one way they could have made this paper a lot clearer as from the problem perspective, because they were saying like the logic for me in the introduction was control theory has been super useful in other fields. Let's use it in language modeling. But if they had framed it in terms of like safety and truthfulness and all these other things instead, and said like we want to find ways to exclude things from the reachable set, I'd be like, oh, that's a really cool use case for this. But they don't really mention it anywhere. So I definitely think that could have been a better way of framing it.
I think, thank you, Anna. Bye. Thank you for joining. I think that what happened was they came up with part of the idea of this. They wrote a paper, they put it in for review. Then the reviewers were, like reviewers can be, go, yes, but you should do all this extra stuff. And so at that point, they started formalizing the control theory element of the paper more. And then they started running the last 2 experiments. And then they actually started getting onto something. So essentially, they probably ran out of time.
Okay.
Yeah. So, and then just for another kicker, so this paper's been peer reviewed, but I don't think it was published. So I think they missed the actual deadline for IC iClear. Yeah. Yeah, I liked it, and it's. I'm frustrated that I can't get some of the code going and that I can't understand it to another level. But I thought it's a good piece of work. They've certainly put a lot of effort into it. Yeah.
It'd be really interesting if they could come up as a follow-up from this with some kind of training objective where you could give a model sequences and prompts, and that would force the model to be unable to generate them. Just maybe not like all of them, but just examples or something like that. That would be really interesting if we could do that.
Even if it's a baby model, right? It's a baby model trained on 4 pages of, some small data set, but just totally from the control theory point of view. Are there any other questions or comments?
Cool. If not, then thanks, Dwane. Sorry about the technical difficulties. We'll have to look into that.
Absolutely.
Maybe next time we'll, for outside people collaborating, I was thinking next time I'll join 15 minutes early and just message you to make sure that it's presenting correctly. But anyway, thank you. This was a really interesting paper.
Okay, good. Thank you.
Definitely. Thanks a lot.